this project we'll be talking about static electricity. Okay, first it's developed by Robert J. van de Graaff in 1929. Okay, first this is the earlier prototype that he built, and this is a newer prototype. So now I'll pass on to Dexter.
Okay, see, this is a Van de Graaff. This is the conventional one, but there are two types of Van de Graaff actually: the conventional one and the dyed and the triboelectric series Van de Graaff. Basically, this Van de Graaff consists of two metal rollers, which one of them is inside a hollow metal sphere, and these two metal rollers are connected by a belt of silk or similar flexible dielectric materials so that they do not conduct electric charges. The electric charges will be around them. This belt is used to transfer the charges from upper roller to a lower roller, which normally the hollow sphere will be positively charged, and the lower roller will be negatively charged, will be connected to the sphere, which this also can be called as the earth. When the upper roller and the bottom roller rolls with the belt, they have friction force around. They have friction around them, which charges them to be positive and negative, which one has a higher potential than the other. Thus, this positively charged will go through the upper electrode, and it will be around the surface of the hollow sphere. You can see this is the triboelectric series, and this Van de Graaff, this second Van de Graaff, is based on the triboelectric effect, which basically Van de Graaff is the electrostatic is created by the friction between the belt and the rollers, which is made of insulators at different positions on the triboelectric series, which the higher they are, the higher they are positively charged, and the lower they are, the higher they are negatively charged. To increase the effect of the spark, the further away the two materials are from each other on the series, the greater are the energy transferred. Let's say we take glass with PVC, which they are very, very far away, and the spark you will see is very, very big. Besides that, these materials become electrically charged when they come in contact with other materials through friction. In simple explanation, when two objects in this series rub against each other or other materials, they get charged positively or negatively. This is because electrons are transferred among the materials, which causes a spark. Okay, as you can see here, this is our Van de Graaff that we built for like almost 3 weeks, and first we thought it did not work because there is no effect on our hand, or there's no static charges that we can see through, like when our hair from our hand get attracted to it, or when the spark, we can't see any of that. But we just realized that there is actually static charges around this metal sphere, because when the belt moves later, the dust that comes out from it, it actually gets drawn all onto the sphere. As you can see here, I don't know whether you can see, but it comes out from the tunnel. Now I'm going to show you how it works, and hopefully you all can see the dust sticking towards this sphere. I don't know whether you all can see it or not, but it is sticking. It's very, very tiny, but it's getting attracted to the wall as we speak now. As you can see here, this is the wire that will transfer the charges from the belt to the metal sphere. And this is the belt that carries the charge. As you can see, this is actually the upper roller that has aluminium foil wrapped around it. In the triboelectric series, this is at the positive side, which is very high, and this is the Teflon tape, or also you can use a PVC tape because it is negatively charged. It is at the bottom roller, and actually these two rollers are so-called connected using this belt. It's a rubber belt. They use rubber belt because they use
in between, right? Which is in between the
not
tripod.
in between, because a rubber belt it's not a conductor. It's an insulator. So that's why we use rubber belt. So when this belt turns, it produces friction from here and here. This is positively charged and this is negatively charged.
Okay, the Van de Graaff is originally used as power supplies to make the particles in Large Hadron Collider to accelerate at a very great magnitude. The early atom smashers consisted of a VDG machine connected to a long vacuum tube for the particles to accelerate in very high velocity. As you can see, this is the current Van de Graaff generator integrated with a particle accelerator. The generator produces the high electrostatic fields in a scale of megavolt range that accelerated the particles.
Okay, next, the application of Van de Graaff is big Van de Graaff is not only used in science fair. You put the hand on it and the hand comes up. It's actually used widely to power high energy X-ray machines. These high power X-ray machines powered by the big Van de Graaff is used to make X-ray photos of the locomotive engines, as it can see through the whole engine of what's wrong with the engine, and it also can be used to treat cancer with radiation, and also used to sterilize food with gamma rays. Okay, now we'll talk about Franklin's motor, or the electrostatic motor, all also known as capacitor motor. These motors are different from the conventional electromagnetic motor. This type of electric motor is based on attraction and repulsion of electric charge, and it is developed by Benjamin Franklin. That's why it's called Franklin's motor, but also developed by Gordon, which originally used to power bells and other small devices. This is the formula of the maximum possible power output that can be derived from the electrostatic motor, which is the F is the rotation frequency, V is the field volume, epsilon R is the dielectric constant of the filling, and E is the peak of electric field. To increase the maximum power output based on the formula, we should increase the frequency of rotation, which is rotating it with a higher velocity, which need a higher current and higher potential, and also the electric field is the easiest to be manipulated. Forces that generate the power do not wear down the plates, resulting in a long-term and stable method of energy generation. Okay, this is the representative of the Franklin's motor, which later we'll see the video of the real Franklin motor, which we built using beer cans, plus paper cup, and 2 aluminium foils like that. Which this is the stick that holds the cup when it spins as the motor, and this is just a simple diagram of it. These are the cans, like I said. So these two will be connected to the fly sweater because it produces a very high voltage, just like the Van de Graaff generator. But we use electric fly sweater because our Van de Graaff didn't really work. So these will be positive and the other than negative. So this positive and this would be negative. So this side is a very high positive potential, which this aluminium foil is naturally neutral. It has a balanced positive and negative charges. So when this side is very, very positive, the positive in here will be pushed to this side and the negative will be attracted to the positive. Then we will see sparks coming here, very small sparks. With these two will cancel each other, and here will be positively charged. Which positive and positive, they repel each other, the cup will turn. Same for this side, is the same theory. When this is a very high negative potential, the negative will be pushed away, but the positive charge stays here because, well, positive can't move, this proton, it can't move, and so these two attracts and electrons will jump. Electrons will jump from higher potential to lower potential. So then this whole pipe is negatively charged. So negatively charged and negatively charged, they repel, so the cup turns. When here turns here, this is positively charged, it will be attracted to the negative pole, and the negative pole will be attracted to the positive side. And the process repeats until the cup turns very, very fast. The cup actually does not slow down, it increases into a very, very high velocity, but due to power loss, due to the friction and the mechanism of the thing and the air turbulence, which causes it to reach only at the maximum velocity. But if you put this inside a vacuum without air, this cup will turn very, very, very fast. Here, this is the Franklin's motor, which is running now at quite a high speed, but it could be higher if there's no air turbulence or there's no friction from the rod, which in an ideal Franklin's motor, which they put it inside a vacuum chamber which has no air, the Franklin's motor would turn at a very high speed and the speed keeps increasing. So we have 3 electric fly sweater here that I connected in series to give a higher potential voltage between these two cans, which we can see here. The spark is very visible. You can see the spark. So yes, this can is negative and this can is positive, which this cup actually has 2 aluminium strips. When one of the aluminium strip is facing this negative side, the electrons will be pushed towards this side and the protons will be this side. So this can is a very negative charge can, so the negative charge will get transferred into the aluminium strip, which makes this negatively charged, which negatively charged can and the negative charge like aluminium strip will repel. So when it repel, it moves the other side. When it moves the other side, it gets attracted because negative gets attracted to positive side. So it gets attracted. The negative will be transferred into the positive side, and all the negative charge will be transferred to the positive can, which leaves the aluminium strip to be positively charged. Which positively charged strip and the positively charged can, they repel each other to the other side, which the process will happen again and again until it turns at this speed. Okay, after seeing how we demonstrate the Franklin's motor of how it turns, now we'll talk about the application of it. The application of it is electrostatic motor is commonly used in micromechanical systems to create a drive voltage of less than 100 volts. Besides, with this, it has a very, very steady and low level energy that presents no risk to the circuitry, in which electrostatic motors are also used in computer circuitry because these electronic boards are very sensitive to spikes in power, which a spike in power would cause the circuitry board to burn, which you will make losses. So the electrostatic motor creates a steady and low level of energy that presents no risk to the circuitry. Also, these are on testing. Spacecraft ion drive uses electrostatic force to accelerate ions to generate forces to create motion, which will levitate, which will make them fly up and fly straight. One of the examples of such thruster is breeded electrostatic ion thruster, which uses xenon gas.
Okay, so Franklin's bell is an early demonstration of the electric charge, which shows same charges repel and opposite charge attract. So for this example in the Franklin's bell, when the metal ball touches the negative bell, electrons will be transferred to the metal ball, thus making the metal ball negatively charged, and in result it will make it repel and swing to the positive bell. And when the negative metal ball touches the positive bell, electrons from the metal ball will jump into the positive bell, which makes it positive again. Thus, it will repeat itself and make the ringing sound. Okay, so when the metal ball touches the negatively charged bell, electrons will jump into the metal ball, which result the metal ball and the bell to be both negatively charged. And when it's negatively charged, it will repel and swing to the other side. And at this point, the negatively charged ball the electrons in the negatively charged metal ball will jump into the positively charged bell, which is connected to the earth. So after that, the ball will become positively charged and swing back to the negatively charged bell. So the process repeats again and again, which makes the ringing sound of the bell. So now we are going to see the actual Franklin's bell that we made. This is the Franklin's bell. We replaced the Van der Graaff with the fly shutter, and this part is highly negative while this part is highly positive. So when the metal touches the negatively charged beer can, electrons will be transferred into the metal and repel the negatively charged can. After that, it will be swing over to the positively charged can, and the electrons in the metal will jump into the positively charged can. And this will keep repeating itself again and again, thus making it ring like a bell, like the Franklin's bell. That's so the ringing sound.
So in conclusion, static electricity can be visualized in many concepts. It can be visualized in many ways, which we show it in the Van der Graaff and the Franklin's motor and also the Franklin's bell.
So basically the concept is when same charges come close to each other, it will repel, and opposite charges attract.
Thank you.